So thank you, Dennis. So it's now my pleasure to introduce Dr. Chaofan Chen. Dr. Chen is an assistant professor of computer science at the University of Maine. He works on the design of interpretable machine learning models that can be understood by human beings. There's been, in the last 10 years, more than 10 years, there's been a major increase in work on neural networks. And these are black box models where you have the input coming in and it churns through a bunch of mathematics and then has an output at the end. And you can't, it's been difficult. How do you understand what these things are doing? How can you trust them? And especially in applications like healthcare, this having trust is crucial. So Dr. Chen has been working on how can we develop methods for understanding these systems. And so Dr. Chen, I'm turning things over to you now.
Thanks, Bob. So hi, everyone. Thank you, Bob, for the introduction. And as Bob says, I am Dr. Chaofan Chen, and I'm currently an assistant professor of computer science at the University of Maine. And my research basically involves developing interpretable machine learning models. So, and part of my work involves developing interpretable deep learning models, and hence the topic of this talk. So in this talk, I'll be presenting a project. It's actually a series of papers, but I'll focus on 3 of them. So basically one of them, but two of them are extensions of the first one. And this is actually a pretty old paper by computer science standards, and it's actually from NeurIPS 2019. And the title of the paper is called "This Looks Like That: Deep Learning for Interpretable Image Recognition." And I started doing this work while I was a PhD student. So imagine that you're looking at this bird and you're wondering what kind of bird this is. And you guess that this is a sparrow. So, but the question really is, how would you describe your thought process? Perhaps the bird's head looks like some prototypical sparrow's head, or perhaps the bellies looks like that of a sparrow, or the feet looks like this, like one that comes from a sparrow, right? So the idea here is that when we humans try to classify images, we might focus on different parts of the image, and we tend to compare them with some mental image of how we conceive this kind of thing is. So in this particular case, if we are to classify this particular bird, we might say, oh yeah, it looks like a sparrow because the head looks like a sparrow's head that we gain from our experience. But the question here is really how we can formalize this process using, say, a deep neural network or any deep learning model. And this brings us to my first work in this area, which is known as the prototypical part network. And this is from this paper from NeurIPS 2019. And it's a joint work with Oscar and another person who happens to have the same first name as mine, so Chaofan Tao, and Alina and Dr. Jonathan Su, and my PhD advisor, Cynthia Rudin from Duke University. So we applied our prototypical part network model to the bird species identification. And we trained our model on a data set called the CUP 22011, which is the Caltech bird data set. And before I introduce our idea, how we actually build a model that can explain its reasoning to human beings, I would like to frame our work in the related work. So basically, prior to our work, how people approach interpretability in deep learning. So before our work, interpretability or explainability of deep learning models is generally achieved either via something called a post hoc explainability analysis or something called the attention models. And in post hoc explainability analysis, basically what happens is that we'll interpret an already trained neural network by fitting some kind of explanations to how it performed classification. So we have, if you are familiar with this type of thing, you might have heard things like activation maximization, deconvolution, or saliency visualization, right? We have a lot of methods to visualize, oh yeah, these are the salient part. Maybe these are the pixels that are important for the network to classify certain things. And the important part about post hoc interpretability analysis or explainability analysis is that they actually do not explain the reasoning process of how a neural network makes its decision, because the neural network is not trained to develop this explanation, right? We try to fit some kind of mechanism to explain it. That's why there's a post hoc. The name post hoc basically means that we explain the network after we train it. So in contrast, our approach is different from the post hoc explainability analysis in the sense that we do not try to fit an explanation after we train a network, right? We try to bake the explanation mechanism directly into the network architecture so that after training, the network can naturally generate its explanation. So the explanation is part of the network. It's not something we fit after we train a network. And the other area where we have interpretability or prior work develops interpretability is through something called the attention models. And basically what attention models does is that these attention models will often explain classification decisions using something called the attention, right? So what's attention? Basically means that these models tend to point to either the entire object or the important parts of the objects in the input image and say that, hey, the network makes this decision because of this object in the image or these parts of the object in the image, okay? But the problem with just having the attention is important parts, but the network never explained why these parts are important. And here's the difference of our work. And our prototypical part network basically provides a richer explanation by closing this gap, by using both attention and similarity to learned prototypical cases, which will be analogous to something like our mental picture of some things, right? So we use both attention and similarity to prototypical cases. And as a result, our model is not only able to highlight the important parts of an input image, but also justify why it highlighted those parts by drawing comparisons between the highlighted part and the prototypical aspects of each class. Okay. And next, I'll talk about the network architecture of our prototypical part network. So more concretely, our proto-PNet basically introduces a special prototype layer that follows any feature extraction layers. So at the time when proto-PNet was developed, these feature extraction layers were mostly just convolutional layers. But I want to say that since 2019, there have been people trying to use the newer feature extraction mechanisms, such as the visual transformer encoders. But I'll stick with the convolutional layers because this is what the original model uses. Okay, so basically we have a prototype layer that follows any feature extraction layers, and it can be convolutional layers or transformer layers. Okay, and let's look at the prototype layer. The prototype layer basically contains prototypes, or the analogous part to the human being would be the mental image, right? So the prototype layers contains prototypes that can be understood as some kind of representations of the typical parts or typical concepts in each class. So such typical concept might be red wings for the class of red-winged blackbirds. Okay, what happens in the prototype layer is that we compare patches of the convolutional features with each of the learned prototypes. And in the original work, we use something based on the L2 distance. So it's an L2 distance-based similarity function, and the form of the similarity function is listed at the bottom of the slide. And this function is basically monotonically decreasing with respect to the L2 distance. And the idea is that if a prototype is closer, if a patch is closer to a prototype in the latent space in the L2 distance, and we consider them to be similar, and we invert that distance to be a similarity score. And this will generate a prototype activation map, which tells us both the location of the most similar patch, as well as the degree of such similarity, as indicated by the similarity score. So to give you a more concrete example, the top prototype here corresponds to the head of a clay-colored sparrow. And I'll talk about how we visualize different prototypes later. But for now, I'll just give you an example saying that this particular prototype corresponds to the head of a clay-colored sparrow. And given this new test image on the left, our ProPNet model recognizes the upper right corner patch of this input image, which is the head of the bird, to be very similar to the sparrow head prototype. And the similarity score basically is the max pooling of all the similarity scores for all the patches, convolutional patches, through the image. And we use a max pool, and the similarity score here is 3.954. And another important thing about ProPNet is that we design our prototypes to be class specific. This means that when we have a prototype, we designate this prototype to be of a certain class, right? And in our first work, in our experiments, we actually use 10 prototypes per class. And we say that prototypes 0 to 9 will be of class 0, right? Prototypes 10 to 19 will be of the class 1, and so on and so forth. And we have a total of 200 classes in the ProPNet. And I also want to point out that there have been later work, extensions of ProPNet that try to relax this kind of pre-assignment of prototypes to classes, right? Things like ProP-share, there's a model that allows one prototype to be shared across different classes. And there has been other models such as ProtoPool, which basically does something called a differential assignment of prototypes to classes. But this is all based on this original ProPNet. And in the original ProPNet, we basically assign prototypes to classes. So prototypes are class specific at the beginning. And after the prototype layer, every prototype unit basically produces a similarity score. And we have a fully connected layer afterwards. And these similarity scores are weighted in the fully connected layer to produce the output class scores, which are the final class scores for all the classes, all the 200 classes. And as usual, the class with the highest logic or the highest score is the predicted class. So this is the same as the usual regular neural network. And before I move on to talk about the training algorithm of ProPNet, I just want to say that our special prototype layer can be used on top of any deep learning feature extraction layers, including convolution layers or later transformer encoders, and in order to enhance the model's interpretability. And in our experiments in the NeurIPS paper, we integrated the prototype layer with VGG, ResNet, and DenseNet architectures. And the experimental results show that our ProPNet can achieve comparable accuracy with its analogous non-interpretable counterparts. And now I'll move on to talk about how we train our model. So the training of ProPNet basically proceeds in 3 stages, and I will talk about each stage in detail. And let's start with the first stage. So in the first stage, what we do is that we optimize the network for accuracy, which is the cross entropy loss. That's the standard loss we use to optimize classification accuracy. But we also have 2 special regularization terms, which we call the cluster cost and the separation cost, that are shown at the bottom of the slide. So basically, the cluster cost we try to minimize both the clustering and the separation cost. And the minimization of the cluster cost encourages each training example, each training image to have some latent patch, some convolutional patch that is close to at least one prototype of its own class. And the minimization of the separation loss, notice that there's a negative sign in the separation loss because we want to, well, I'll explain that later, but the minimization of the separation loss basically encourages every latent patch of a training image to stay away from the prototypes not of its own class. So the negative basically means that when we minimize this negative thing, we are maximizing what's the thing that's without the negative sign. Right? And the expression there is basically the minimum distance between the convolutional patch of the training image and a prototype not of its own class. So we try to maximize that distance. So that's the separation loss. We try to say that, okay, every convolutional patch needs to stay away from a prototype that's not of its own class. So hence there's the clustering term and the separation term. Okay. And both of these terms will together shape this latent space, the feature space, into a semantically meaningful clustering structure, which will facilitate the L2 distance-based classification of proto-PNet. And the slides here, I'll use the slides here to illustrate this idea. So initially, as you can see, the latent patches, which I use different patches of birds, the latent patches, which are you can understand them as the convolutional patches, but I'm visualizing them using different image patches. So initially, these patches are not clustered. And after going through the first stage of training, after a few epochs of this stochastic gradient descent of this training, the latent patches are now separated into distinct clusters because of the cluster term and the separation term. So in this slide, the triangles will actually represent the prototypical wings, and the circles represent the prototypical heads. And I'm just showing two classes here. And I use the green color here to correspond to the class of painter buntings, which is a type of bird, and the blue color here to represent the class of indigo buntings. So now we have 4 clusters. And also in stage 1 of training, we fix the last layer of the neural network of our proto-PNet by setting the connection between a prototype and the logit of its own class to be 1. And so in our training, we fix the last layer by setting the connection between a prototype and the logit of its own class. Notice that the prototypes are class specific, so we already know the identity of the class. Right? So we set the connection between a prototype and the logit of its own class to be positive 1. And we set the connection to the logits between the prototype and the logits of all other classes to be negative 0.5. And the reason we did that is because the positive connection between a class K prototype and the class K logit means that if something is similar to a class K prototype, right, this will increase the predicted probability that the image belongs to class K. And the negative connection between a non-class K prototype and the class K logit means that the similarity to a non-class K prototype should decrease the class K predicted probability. So by fixing the last layer in this way, we can force the network to learn a meaningful latent space, because if a latent patch of a class K image gets too close to a non-class K prototype, then this will decrease the predicted probability that the image belongs to class K. And what this means is that it will increase the cross-entropy loss of the training objective. Therefore, by building this last layer, by fixing the last layer weight, we are also trying to enforce this clustering structure in this first stage of training. And after the first stage of training, and you'll notice that we have these prototypes, right? But we don't have a visualization of the prototypes. How do we actually visualize the prototypes? So in order to visualize the prototypes, we force these triangles and the circles. These are the prototypes that do not necessarily sit on a training image latent patch. So we basically project them or push them to the nearest training image, nearest latent patch that comes from the training set. And of course, it will project them onto the nearest training image latent patch from the same class as the prototype, right? We don't want to project the class 0 prototype to a class 1 patch. That's not good. So what happens is that we'll project the prototypes to their nearest training image patch from the same class. And the result is shown here. The ones with the bolded borders now represent the new prototypes. So now we can actually associate each prototype with some training image. And in the last stage of training, is the stage 3 of training, we'll optimize the last layer. So remember that we fixed the last layer in stage 1 to be 1 or negative 0.5, right? 1 between a prototype and the class score of its own class, and negative 0.5 between a prototype to all other classes, right? So in the last stage, we'll relax this constraint, right? We'll allow the last layer weights to change. At the same time, we do not allow anything else to change, right? So anything that's the convolutional layer, the feature extraction layer, and the prototype layer will not change, because the latent structure or the feature space has been very well shaped at this point. So we do not want to mess with those things. And instead, we want to squeeze out a little bit more accuracy from our network. So what do? We fine tune the last layer, right? This doesn't affect the clustering structure we just learned, right, in the stage 1 and stage 2. So we can do that. And we allow the last layer weights to change. And there's a special L1 regularization term in the loss function, as you might notice. So this L1 regularization term basically penalizes the connections in the last layer between a prototype and the classes that's not of its own class. Right? Remember that was set to negative 0.5 at the beginning in stage 1. Now we try to impose an L1 regularization to all those connections to make them 0. The rationale for doing this is that we do not want a prototype of class K prime to contribute to the score of class K. We just want the prototype of class K to contribute to class K score. We don't want other prototypes to contribute to the class K score. So we want to make those negative connections 0. Okay. So basically, after going through the 3 stages of training, our proto-PNet will be well trained. And now I'll talk about how we visualize the prototypes. So because of the stage 2 of training proto-PNet, at least we know the training image, right? Where the training image where the prototype is projected onto, whose latent patch, some latent patch the prototype is projected onto. Right? But we need to identify which patch from the training image of that training image this prototype corresponds to. So the way we do that is we visualize a prototype by identifying the image patch that corresponds to the latent patch of the training image where the prototype originates using these 3 steps. Right? First, we pass the training image where the prototype comes from through the network again, through the prototype layer, to generate a prototype activation map. Right? That's the step 1. Right? There's a heat map here. And then we identify the most activated image patch, basically the closest rectangle, the smallest rectangle that encloses this red area. And then we'll use that smallest rectangle that encloses the most highly activated region to be the visualization of the prototype. So this is how we visualize our prototypes. So with all these, the good thing about our model is that we can view the decision-making process of our proto-PNet as if we were evaluating a scoring sheet for every one of the 200 classes in our application. Right? And here, the final score for every class can actually be understood as a weighted sum of similarity scores with the visualizable prototypes of that class. So for this particular slide, we have a test image that's on the left. here. We have a test image. And so we try to compare this test image with every single prototypes that's learned during the training process. And let's focus on just one class, right? So the class is called the red-bellied woodpecker class. It's actually the predictor class in this case. And the slide here shows the top 3 activator prototypes of the red-bellied woodpecker class by this test image. As we can see, our proto-PNet identifies this head region, the red part of the head region, to be similar to this prototype here. And this is the training image where the prototype comes from, the next column, and then with this activation map, right? So the activation map is basically generated by the prototype activation map. It's an upsampled prototype activation map. And the highest score, which is the max pooled score, is 6.499 here for the top activator prototype for this class. And the class connection is the connection, the weight between this prototype and the class score of red-bellied woodpecker. And as we can see, the class score, the class connection is 1.180, which means that this prototype is weighted 1.18 times as important for this class, okay? And then we have this point contributor. This point contributor is the multiplication between the similarity score and the weight, and we get 7.669. And we can do that for every single prototype of this class to get the similarity score, and then the class connection, and then the point contributor by this prototype. And assuming we do that for every one of the 10 prototypes for this class, and then we add up the score, we get 32 points for this particular class, right? So for the red-bellied woodpecker class, this test image receives a score of 32.736. And of course, we don't just do that for one single class. We do that for every single one of the 200 classes. So we can do that for another class, say a red-cockaded woodpecker, right? In this case, the network, you can see that the network focuses on the wing part of this test image, right? It identifies that the wing of this test image to be very similar to the wing of a red-cockaded woodpecker with some quite high similarity score. But as the similarity it's only limited in this wing part, right? It doesn't receive a lot of other similarity. So the total similarity score between this test image to the red-cockaded woodpecker class is only 16.886 points, right? So you can do that for every single one of the 200 classes. So evaluating 200 scoring sheet essentially, and then you pick the one with the highest score. In this case, the highest scored class is the red-bellied woodpecker. It has 32 points. So therefore, our network classifies this image as a red-bellied woodpecker. So this is a correct example, right? So our network classified this example correctly. And I'll show you some more examples. In this particular slide, we have a test image of, let's see, a pie-billed grape, okay? So the same idea is that we compare this test image with the prototypical concept, prototypical parts that are learned from the training sets, right? So we see that the network identifies the head of this test bird to be very similar to the head, prototypical head of this pie-billed grape. And the similarity, the total similarity to this class is 23 points in this case. And of course, we'll repeat this whole process for every single one of the 200 classes. And the second highest scored class has a score of 14.154. So it's a lower, it has lower points. Therefore, this, again, right, the network classifies it as a pie-billed grape. And it's correct, it's a correct classification in this case. And I'll show you another example. In this particular slide, we have a test bird of prothonotary warbler. And it's the same idea, right? We compare part of this test image with the prototypical parts that are learned from the training set that represents this class. And we see that the head part looks like this prototypical prothonotary heads that are learned from the training set. And in this case, the top class has only a similarity score of 9.8, And the second highest class has a lower similarity score of 5.462. So using these three examples, I hope I have convinced you that we can basically interpret the decision process of our prototypical part network in this way. And I want to show you another example, another reasoning process using a example, because I want to show you that what happens when a network makes a mistake in this case. Okay, so for the same test image with a different proto-PNet model, in this particular case, this is the highest score class, right? It's the same test image. And in this particular case, the network thinks that this is a Wilson's wobbler. And again, right, we can see that this is the head part looks like a Wilson's wobbler's head, and the wing looks like a Wilson's wobbler's wing. And in this particular case, the Wilson's wobbler has a similarity score of 9.744, whereas the sorry, this is actually a Wilson's wobbler. I actually yeah, this is actually a test image of Wilson's wobbler. And for the prothonotary wobbler, it actually has a higher score. This is 12.391 because it identifies more similarity between this test image and the prothonotary wobbler, which is the wrong class. But even though the network makes some mistakes here, we can see that we can still see the reasoning process of the network and understand why it makes the mistake. So this is actually very important when we apply a neural network to, say, a medical situation, because when we have a neural network that classifies some medical image, if it makes a mistake, and we can have a doctor to check over the reasoning process and say that, oh yeah, it indeed makes a mistake. So we want to understand why it makes a mistake. And therefore, our network, even though it makes a mistake in this case, it can still be very useful. And another thing we developed is that we can further improve the accuracy of our model by simply having more of the models, right? So this is the idea of ensembling. And a very simple way to combine the prediction of several proto-PNets is simply by adding the logits or the total points together, right? And I'll use the previous example to illustrate why this can improve the accuracy. So let's go back to the previous example of classifying the image of a Wilson's wobbler. As you can recall, the first model predicts correctly, right? It predicts that the total points is Wilson's wobbler, right? The Wilson's wobbler has a higher score, 9.8, and the second highest score, which is the prothonotary wobbler, has 5.4. And the second model predicts incorrectly. It predicts the prothonotary wobbler, right? Whereas the total points to the correct class is 9.7, but the total points to the wrong class, prothonotary wobbler, is 12.391. And if we have a combined model, say we combine proto-PNet 1 with proto-PNet 2, by adding their class points together, the total points to the correct class is 9.8 plus 9.7, which is 19.58. And the total points to the incorrect class, prothonotary wobbler, is 5.4 plus 12.391, and we get 17 point something, right? So as you see, the Wilson's wobbler now has a higher score. Therefore, the combined model will now predict correctly. Therefore, we can simply by having more proto-PNets and adding their logits together, we can improve their accuracy, and we can treat individual models still as scoring sheets, right? So it's still somewhat interpretable in a sense. And this slide shows the accuracy comparison of our proto-PNet model with the analogous non-interpretable counterparts and with attention-based interpretable models. So the top table here compares our proto-PNets with the base model, right? The baseline models, and for various base architectures. As you can see, by introducing this prototype layer and forcing this latent structure, this feature learning, the accuracy does not change too much, right? We don't have too much decrease in accuracy. And in some cases, the accuracy actually improved over the baseline. And the bottom table here compares the proto-PNETs with the state-of-art models at the time of 2019, by the way. So, and we combined some models, right? We basically have we combined 3 proto-PNET models and use that to compare with the state-of-the-art at the time of 2019. And the reason we did that is because if we just use a proto-PNET, it's actually not very fair for our model, because a lot of the state-of-the-art at that time, for example, BCN, it actually combines 2 CNN backbones, right? So if we just have one basic backbone, it's not a fair comparison. So we basically use a combined model to compare with the state-of-the-art. Okay, so now we can we want to analyze the latent space or the feature space of our learned network, because it's an important thing. We want to see that the feature space is indeed well formed, right? Because we don't want to just have the accuracy. We also want to be sure that indeed the prototype is close to the nearby examples that are close to the prototype really looks like the prototype, right? That's something we want to show here. So the slides here shows that the latent space or the feature space learned by our network is indeed well shaped. So we have 2 sides of the slide. The left side of the figure, which is the left side of the figure, the slide shows the 3 nearest prototypes to a given test image. And we have a test image of a Florida J and a test image of a cardinal. And for the Florida J example, we can see that the nearest prototypes of the Florida J are all the wings of the Florida J. And the nearest patches, the closest patches that's close to the prototypes are indeed all localizes the wings of that Florida J. And for the cardinal example, the most activated prototypes, the most similar prototypes are all the heads of the cardinals. And indeed, we can see that the most similar patch of this cardinal test image to each of the 3 head prototypes are all the heads of this cardinal. So this is something we call the local analysis, where we give a test image and we try to find the closest prototypes to a given test image. And on the right-hand side of the slide, we have something called we call global analysis. So the right-hand side of the figure basically gives you each prototypes, right? We want to find the nearest test patches to each single prototype, right? And we show 3 prototypes here. As you can see, the nearest image patches, whether from the training set or the test set, right? The nearest training patches or test patches to the first prototype in the slides are all heads of the black-footed albatrosses. And this prototype is a head of this prototype basically represents the head of the black-footed albatrosses, okay? And the second prototype is basically, in this case, is the yellow stripes on the wings of a golden winged warblers. As you can see, the nearest training patches and test patches are indeed all the wings of the golden winged warblers. And for the third prototype is the feet of some gull. And the nearest patches to the third prototypes, either from the training set or the test set, are indeed the feet of some gulls. Okay, so it is generally true that the nearest patches of a prototype all bear the same semantic concept, and they mostly come from those images in the same class as the prototype. So we can call this a success. And however, sometimes, right, we do have prototypes that are not very nice. In this particular case, right, since we use bird images to train our model, sometimes the prototypes will pick up things such as twigs or sky or some background. Okay. So in other words, we may encounter prototypes, right, where the nearest training patches may not come from the same class as the designated class of the prototype. And when this happens, these prototypes usually correspond to some background objects or background patches, right? And in this particular slide, we have some examples of such prototypes. And we think that these prototypes are undesirable because it can potentially confound the reasoning process of a prototypical part network. And to remove this kind of background prototypes, we have developed something called a pruning procedure. And what happens is that the pruning algorithm will start by finding the k nearest latent patches of the training images to each prototype. And because we know the labels of the training images, we will know the class labels of the k training images where the k nearest latent patches to each prototype will come from. Right? So out of these k training images that's close to a particular prototype, if we find that a lot of them come from different classes, then we know that this prototype is probably a background prototype and we should remove them. So this is basically our pruning procedure. And after we do the pruning, this slide shows you that if we retrain, we fine-tune the last layer after we prune the prototype, we can fine-tune the last layer again, right? We can basically recover the same accuracy as we had before the pruning. So this will actually offer us a way to reduce the number of prototypes per class. Yeah. And the last part of this talk So we extended our work in ProtoPNet to the study of mammograms. In particular, we focus on the problem of identifying mass margin types of breast tumors in mammograms. So the goal here is to learn a set of visualizable prototypes that correspond to different BI-RADS features. So BI-RADS features are those features that are used by human radiologists to determine if someone's tumor is cancerous. So, and a particularly important BI-RAD feature is the mass margin types. So we can have BI-RAD features such as speculated mass margin types, which is actually very cancerous. If you have that, it's probably cancerous. And the circumscribed mass margin, and that's a different BI-RAD feature. So we basically try to develop a model to use this model to learn the BI-RAD features. And the idea here is that if we learn prototypes of these different mass margins, similarities to these prototypes will indicate the presence of these particular BI-RAD features, and we can use them to predict the malignancy of the breast lesion. So the paper describing our work is known as a case-based interpretable deep learning model for classification of mass lesions in digital mammography. And this has been published in Nature Machine Intelligence in 2021. And it's a joint work with Alina and Fieders and Chaofan Chen and Ying Hao and Joseph and Cynthia Rudin from Duke. We applied this to identify the mass margin types and malignant tumors in mammograms. So our model is basically called IAIA-BL, which stands for Interpretable AI Algorithm for Breast Lesion. So our model uses a similar model architecture as a VGG16-based ProtoPNet. Right? We use that to classify the mass margins. And in addition, we also have a second fully connected layer that predicts a malignancy score from the scores of various mass margin types. Okay. And the reasoning process of this IAIA-BL is very, very similar to ProtoPNet. Basically, it follows the same procedure, right? This part looks like this prototypical part that's of this class. Therefore, it contributes this particular score to this particular class. So it's a very similar classification idea to ProtoPNet. So what's new? The new thing with this work is that we are faced with something called a confounding issue here. So working with mammograms or any medical image is actually very challenging because the biggest issue is that is something called confounding, or right for the wrong reason, right? The network can predict certain things correctly, but the reason it provides can be crappy, right? So for example, you can have a model that's trained on medical images, and you say that, okay, the important part that why I classify this as a speculative mass margin is because of this region, right? But the region it provides as the reason might not even be on a mass margin. So we know that this is not good, right? So this is known as confounding. It means that even though the network provides the right prediction, the explanation it offers is completely off, right? It's not medically relevant. And we found that if we directly apply the original proto-PNet training algorithm and apply it to train it on medical images, it basically leads to medically irrelevant prototypes, right? And part of the reason is also because we have a very small data set, and also there's no pre-training for medical images. Unlike pre-trained, we have pre-trained models on ImageNet, which is already very powerful for natural images. But for medical images, this kind of thing is very difficult. So we often end up with prototypes that represent healthy tissues. And the idea is that they are very similar to the background prototypes we see in the bird images, right? We basically, but except in this case, right, all of the prototypes are background prototypes, right? Which means that if we just apply the pruning algorithm I discussed, this will be useless because every single prototype is not relevant, will be pruned away, right? And we are left with no models in this case. So we definitely need a way to help our model focus on medically relevant regions. And the solution we developed for this particular problem, the confounding issue, is called the fine annotation loss. And the basic idea behind this fine annotation loss is that we will penalize prototype activations on medically irrelevant regions of mammograms during training. But the issue is that how do we know which regions are medically relevant or irrelevant, right? If we just use unsupervised training, this is impossible to know. Therefore, we have to introduce some extra form of supervision in this case. And the way we did that is we asked human experts or radiologists to mark the medically relevant regions on mammograms. And the key here is that this is different from segmentation because we are not performing segmentation here. And another key difference between this particular work and the segmentation is that the markings from the human experts do not need to be perfect. They can just be some rough drawings, right? Rough drawing around the medically relevant regions. This is completely okay. And the idea here is that any region that's outside the expert markings, which will use the MI to denote that, this is also known as the mask. Any region outside the expert markings, we'll treat them as the irrelevant regions, right? And we want to minimize the prototype activations outside the medically relevant regions, outside the expert markings. So if you look at the formula for this fine annotation loss here, we have two terms here. The first one is basically the MI is the region that's outside the expert marking. So it's the irrelevant region, right? And PAM is the prototype activation map. So the idea here is that if the prototype activates on the region that's outside the expert marking, on the irrelevant region, we should minimize that. We should minimize this part of the loss, right? We don't want that, right? And this should be minimized for the prototypes J, that's of the correct class. Hence this part J, which is class PJ is equal to the correct class here, the correct margin class here. Right? What about the wrong class, right? For the wrong class, if we have a prototype PJ that's not of the correct class, that's not of the ground truth class, right? We want to minimize the prototype activation everywhere, right? We don't want this prototype to activate at all. Right? So this is the basic idea behind fine annotation loss. And we have one more issue here. Asking human experts to mark the medically relevant regions on mammograms is actually a very time-consuming process, right? So we don't want to do that. So the observation here is that the question here is really, do we need the markings for all of the images in our training set? not necessarily, right? We don't need that. The reason is that because if we have an image that does not have an expert marking of medically relevant regions, we can think of the entire image as being medically relevant, right? So we can still apply a fine annotation loss, but this is the trivial case, right? Basically, everywhere is possible, right? It's possibly medically relevant, but it's the trivial case, right? So in fact, we only ask our radiologists to provide markings for only 9% of the training images we have. And now I'll talk about the effect of introducing this fine annotation loss. The first one is a qualitative comparison. So we'll compare the class activation maps of the various models on various input mammograms. Right? So the way we compute the fine annotation loss is this, right? For the way we computed this class activation maps for different models goes like this. For the IAIBL and the baseline proto-PNET model, we compute the class activation map of a given input mammogram by using a weighted sum of the prototype activation maps for those prototypes that belong to the predictor class. Right? So basically, we just add up the prototype activation maps for the predictor class. Right? And we use a weight to weight each prototype activation map. And the weight comes from the last layer. And for the uninterpretable neural networks, such as the baseline VGG16 model, we use the gradient weighted class activation map, or GradCam and GradCam++. The result here is quite stunning because our IIBL using the fine annotation loss is able to look at the lesion, in particular the margin of the lesion, when classifying the type of the mass margin. Whereas if you look at all other models, it's basically looking at random places and you don't really know where they are looking at. So basically this shows that they really don't know, they really have no clue of what they are classifying here, even though they can offer correct prediction, but the reasoning is completely garbage. And we also develop a quantitative way to evaluate the interpretability on those images with expert markings. So the metric we developed is called the activation precision. And the formula here you see is the activation precision for a single prototype PJ on a single image Xi that has the mass margin class Yi margin and comes with the expert marking 1 minus Mi. Okay, so if you look at this formula, I just want I'll first introduce some notation here. The T tau is basically a threshold function, where the tau in this case is the threshold. Right, we set the threshold to be 0.95. So T tau is basically the function that returns the top 1 minus tau times 100% of the input values as 1, and the bottom tau times 100% as 0. So tau equal to 0.95 means that this threshold function returns the top 5% of the highly activated pixels, right, as 1. It marks the top 5% most highly activated pixel as 1, and all other pixels as 0. So if you look at the new denominator of this formula, what happens in the denominator is basically this sum is basically counting, right, the number of pixels that are highly activated. And what about the numerator? The numerator here is basically the number of pixels that are highly activated that's also in the medically relevant region. 1 minus Mi is the medically relevant region. So taken together, this activation precision measures the proportion of highly activated pixels that are medically relevant. Okay, so the higher the number, the more medically relevant the prototype is. That's the basic idea. And we can extend this definition of activation precision on a single prototype on a single image to a whole data set D prime with expert markings and the whole set of prototypes P by basically taking the average of this activation precision score on every single one of the prototype and the image. Right? We take the average of them. And this is actually a measure of interpretability in the sense that the higher the activation precision, the better a prototype or a set of prototypes is at detecting medically relevant features for mass margin classification. As you can see, using this metric of activation precision, our IIBL trained with fine annotation loss is able to achieve the highest activation precision of 0.41, which tells us that it's indeed looking at the medically relevant regions. So what about the performance of this model? So we measure our performance using AUROC, and we find that the performance of the IIBL model is as good as or better than the original ProtoPNet and the uninterpretable VGG16 network, which is the baseline network. And this ROC curve here is the ROC curve for the circumscribed margin class. And for this particular class, our IIBL has the highest test AURC for this class. Okay. And this is another class. This is an indistinct margin class. In this particular case, our IIBL has comparable AURC with a black box model, the black box VGG16, and it's better than the original ProtoPNet. And this slide shows the AURC, the ROC curve for the speculator class, and our IIBL beats the black box network in this case. So the takeaway is that by introducing this fine annotation loss, our model is able to learn the medically relevant regions and do as good as other networks, or even better than the original networks in terms of performance, AURC performance. And finally, I'll close my talk with a more recent work that I did with my former undergraduate student, John Donnelly, and Alina who's a PhD student at Duke. So our work is known as deformable ProtoPNet or deformable prototypical part network. Right? And this was published in CVPR 2022. And it's the same application of identifying bird species. So the new thing about this model is that we basically augment each prototype with 4 or 9 prototypical parts, right? So we treat a prototype, now it's not one single part, right? A prototype consists of 4 parts or 9 parts, okay? And if we have more than one part, right? And as the name suggests, right? We can deform the prototypes. So depending on the input image and the position on the input image, our deformable ProtoPNet is able to deform the prototype when comparing its prototypical parts with the input image features. So this gives us another way to learn the deformation of a model, the deformation of different test images. Right? So to close this talk, so in this talk, I presented my work in developing interpretable deep learning models using case-based reasoning and prototypical examples. So I have talked about prototypical part network, the original ProtoPNet in detail. I have presented the application of this ProtoPNet to medical images, which is the IIBL model. And I have also briefly mentioned the latest work, which is a deformable ProtoPNet. And if you have any questions about these works, you can contact me at my email address, which is shown on this slide, and I'll finish my talk and open the floor for questions.
Thank you, Chaofan. So I'd like to start with, I've got a couple of questions myself, so I'll start things off. First question is about the classes. You started with 200 classes. I'm wondering where those came from. Did you select particular images from ImageNet, for example, or where do you get the classes? That's first question. Second question is about with the medical images. Where you ask for the doctors to annotate particular ones. I'm wondering, but they only need to annotate 9%. I'm wondering about active learning and systems where the system is identifying something and you just play an image to the doctor and the doctor says, no, this is wrong, and through active learning, it's able to reduce the amount of annotation that you have to have. That's question 2. And the third question is about combining natural language information with the images in order to help the system use the other information to focus where it should identify prototypes.
Yeah, so for the first question, it's actually the CUP 200 2011 is basically its own data set. It's not ImageNet. It's a data set from Caltech, and the 200 classes come from the data set. So it's not, we didn't collect the
Okay.
200 classes from the ImageNet, but the data set comes with 200 classes of different birds. Yeah. And the second question was the medical
Active learning.
Oh, the active learning. So yes, what we presented is what I just presented is not active learning. It's basically we don't. Yes, I believe that if we use active learning, we can further reduce the amount of annotations. So what we did was basically just have 9% of the images annotated beforehand. There's no active learning
That's okay. But I think active learning would be an interesting thing to apply to this.
Yes, exactly. Yes, I agree with you. But that's not what we did. And the third question is, sorry, I forgot.
Using natural language to help the system figure out where the prototype should be, where should focus its attention.
Yes,
and things like when I'm looking at the red-breasted thing or the thing, it wasn't the particular part of the shape so much as the color that stood out as salient, and so that was another thing.
Yes, so as you have noticed, none of our models have anything to do with natural language processing. They don't have any natural language processing capabilities, and it's a good future research direction. Yeah, so it's definitely a very good future research direction. And I know that there have been work on basically vision language combined models. Large vision language models, but these are not what I presented. Yes, but I agree that these will be a good future research direction to improve the model. Yes.
Okay, thank you.